Have you ever seriously tried to imagine building a quantum computer? I mean, it sounds like something straight out of a sci-fi movie, right? An impossibly complex machine. But here's the thing. While it is, for sure, one of the biggest engineering challenges of our time, the actual blueprint, that's something we can get our heads around.
So, let's peel back all the hype, all the mystery. What does it really take? We're going to break down the key parts, the biggest roadblocks, and yeah, the mind-bending physics that make it all tick. Okay, let's just dive right in.
Think of this as our own little build guide, an instruction manual, if you will, for putting together a machine that literally operates at the very edge of what we consider reality.
So here's our game plan. We'll start with the big picture, the quantum blueprint. Then we'll tackle the three main steps: making the qubits, creating the deep freeze environment, and then correcting all the errors. And finally, we'll see how it all comes together.
All right, so before we even dream of building anything, we have to wrap our heads around three absolutely massive engineering hurdles. These are the fundamental problems that everyone in the field is trying to solve right now.
Okay, step one. Every computer needs a basic unit of information, right? For the computer you're using now, that's a bit. For a quantum computer, we need to build something way more powerful and a whole lot more fragile. We need to build the quantum bit, or qubit.
So what on earth is a qubit? Well, it's the secret sauce. You know, imagine you flip a coin. While it's spinning in the air, is it heads or tails? In a way, it's both. A qubit is just like that spinning coin. It can be a 0 and a 1 at the exact same time. And that wild property? It's called superposition.
This is such a great way to think about it. A classical bit, that's just a light switch. It's on or it's off, a 1 or a 0. Simple. But a quantum bit, that's more like a dimmer switch. It's not just on or off. It can exist in all those states in between, all at once. And that ability to hold so much more information is what could make quantum computers so unbelievably powerful.
Okay, so say we have our qubits. Great, but we can't just slap them on a regular motherboard. To keep them in that fragile quantum state, we have to go to our second and very extreme step. We have to create an environment colder than, well, colder than pretty much anything.
Just look at that number. 0.01 Kelvin. That is just 1/100th of a degree above absolute zero, the point where all atoms are supposed to just stop moving. To put that into perspective for you, the vacuum of deep space is a kind of toasty 2.7 Kelvin. So yeah, we have to make our computer colder than the coldest parts of the universe.
So why the ridiculously cold temperature? Well, think about it. Heat is really just vibration. It's atoms jiggling around. For a qubit, any tiny vibration, any stray bit of energy, what scientists call noise, can instantly knock it out of its special superposition state and just ruin the whole calculation. This deep freeze is basically our way of telling all the atoms to just be quiet and stay perfectly still.
And that brings us to our third and final step. Because even in that perfect, quiet, super cold environment, things still go wrong. A qubit can just flip or lose its quantum state for no reason. So we have to build this incredibly complex, real-time spell checker, a guardian system that can find and fix these errors without messing everything up.
This quote really nails the problem, doesn't it? A quantum state is so fragile. But here's the paradox. The very act of looking at a qubit to see if it's right or wrong, well, that act of looking at it can destroy its quantum state. So how in the world do you check for an error without actually looking? It sounds impossible. Well, here's the incredibly clever three-part trick. First, an error happens. They call it decoherence. Then, and this is the genius part, instead of looking at the qubit itself, the system uses its neighbor qubits to spot the symptom of an error. It's kind of like finding a footprint in the mud without ever seeing the person who made it. And finally, once it knows what's wrong, the system zaps the faulty qubit with a tiny, precise pulse to nudge it right back where it belongs. And all of this has to happen in a fraction of a second. It's just amazing.
So there you have it. That's our blueprint. Building one of these isn't about screws and bolts. It's about solving these three massive, fundamental challenges that push the absolute limits of physics and engineering.
So let's just recap the three pillars, the big takeaways. First, you have to somehow build these perfect, stable qubits. Second, you have to isolate them in an environment that is colder than deep space. And third, you need a lightning-fast error correction system to act as a constant bodyguard for their quantum states. If you can master those three things, you've built a quantum computer.
And you know, that really brings us to the biggest question of all. After seeing just how ridiculously hard this is, I mean, the extreme physics, the insane engineering, why bother? Why are thousands of the smartest people on the planet dedicating their entire lives to this? Now that is a question worth thinking about. Because the answer, well, it could change everything.